Okay, we have here today an interesting integral. We've got the integral from 0 to infinity, x cubed ln x e minus 2x dx. Okay, we've got a lot going on here, and this is kind of similar to a few other problems I'm doing. I'm doing a few variations on the same kind of problem. Now for this one, we could actually do it by a formula. I don't really want to do it that way, even though that would be much faster. It's just that I want to get into some of the details on how this works. So what I want to do is set up Finemans Trick on it. We'll create a parameter. I think what we'll do it for this. We'll set up a function f of a. And the way we'll do it, see the ln x is kind of complicated. So I'm going to start with something that doesn't have that. We can do something like x to the a e minus, and let's parameterize this as well. We'll make that into an s. So when we come back later on, we're going to have a equals 3, s equals 2, and we can just plug in. So doing it like this, I've set up a function where this is something we know, or we could say there's a nice formula for this. This is actually a Laplace transform. So this is actually a Laplace transform of x to the a. If you're not familiar with Laplace transforms, I'll give a link. I have a playlist on this so you can see where we derive this formula. So the formula for this thing is just going to be s to the a plus 1, and we're going to have gamma a plus 1 in the numerator. And then for Finemans Trick, what we're going to want to do on is we're just going to want to differentiate this function. Over here, we'll differentiate on both sides, but we're differentiating with respect to a. So when we do this with Finemans Trick, what happens, we're going to differentiate as a partial. We bring it inside the integral. I'm just going to kind of do this quickly on the fly. But all this stuff here, this is going to be a constant with respect to a. So when we differentiate, we're really just worried about differentiating this. So we'll leave this out front. Differentiating this by formula, we get x to the a ln x dx. So what we've done here is we've generated an integral that's in exactly the same form as what we want. So if we can figure out this thing and have some kind of formula for it, we can take our constant values, plug it back in the end, and we'll have a solution for this. So the next part is differentiating the right side of the equation. This is going to be quotient rule. And so first we're going to have the derivative of gamma function. So that's a little weird. We'll just leave that for a second. Then we have the denominator. We'll just bring that along. And then we have gamma a plus 1. Then derivative of this, which is going to be s a plus 1 ln s. Just using the same formula we used over here. And now we just want denominator squared. So we have s a plus 1 all squared. But then we've got something in common, this s a plus 1. If we factored it out, it's going to cancel all over the place. We can cancel this with one of these. And we're getting somewhere, but the part that's kind of gnarly is this right here. It's kind of weird to think about the derivative of the gamma function because, the gamma function can be expressed as an integral, but then how do we simplify this? Well, what we can do is we can look at our formula for the digamma function, which is related to the gamma function. It just says the digamma of x is going to be the same thing as the derivative of gamma of x over gamma of x. So if I just take this and multiply through by gamma of x on both sides, this cancels out, and now we have an expression for this thing right here. So we'll plug this in, just plugging in a plus 1 into it, so we have gamma a plus 1, then digamma a plus 1, minus another gamma a plus 1 ln s over this s to the a plus 1. So at this point, we basically have our formula for this kind of integral. There's some simplification we could do on it. I mean, we could factor out this we have in common. There's also kind of a question of what we do, the digamma function. We have some different formulas for that based on if it's an integer or not. But I think what we'll do is let's just start plugging in and see where we can get with it. I think that's how I feel like dealing with it. I don't really know. So let's give that a try. But when I do this, let's actually factor this out. So for gamma a plus 1, we'll factor it out and plug in at the same time. So you plug in 3, and we're pulling gamma of 4 out of it. Then this is going to be digamma of 4 minus natural log. We'll plug our s value back in. So this is going to be natural log of 2 over 2 to the 3 plus 1. That's a 4. So 2 to the 4, let's clean that up right away. 2 to the 4 is the same thing as 16. Now gamma of 4, we can reduce that with a factorial. So we have, for that we have this formula. If n is an integer, let's do this, let's do it as n plus 1. So if we have gamma of n plus 1 and n's an integer, this is the same thing as n factorial. So what that allows us to do is for gamma of 4 to write it as 3 factorial or just 6. I should probably do an equal sign there just so it's not confusing. So this thing is just a 6. Then next I want to deal with digamma of 4. It's something kind of similar. We have a recursive formula. It's not going to be as clean as the factorial. For this, when n is an integer, like we have it here, it's more complicated if it's not an integer, but we're lucky it's an integer. So for gamma n plus 1, this is going to be the same thing as a harmonic number of n, reducing that by 1, minus the Euler-Mascheroni constant. This is something like that, close to 0.577. And you might wonder, what is this harmonic number? It's pretty easy, especially for small numbers. It's just going to be, it's defined as like a series of 1 over, let's use k, I think. Yeah, I want to use k because n is going to be the upper limit. So if we do this sum from k equals 1 to n, then we can just kind of, then for something like 4, if our upper bound here is 4, we can just kind of count it out. So in our case here, I mean, actually we could write this as 3 plus 1. So our n value here is going to be 3. So we're just going to be summing here from 1 to 3. Then just kind of plugging in, this is going to be the same thing as 1 over 1, 1 over 2, 1 over 3. If you get a common denominator of 6 and add it all up, this thing is going to be 11 over 6. So what that allows us to do is for digamma of 4 right here, we can just plug in, and this is going to be 11 over 6 minus Euler-Mascheroni constant. So let's see if I can put it all together with just this small amount of space over here. That 3 factorial, I'm going to write that as a 6, and then I'm just going to distribute it in here. So multiplying 6 times 11 over 6, we just get 11 minus 6 times the Euler-Mascheroni constant minus 6 ln 2 over 16, and that's it. And hopefully that fit on the board. Let me move things up a little bit. So there you go, really interesting technique, just Finemans trick. We can generate the natural log x, or you could kind of go directly to a formula like this. You could actually simplify this formula. I think I went over it in another video. You could simplify the formula more by factoring or noticing it's an integer value. So you have different variations. Especially the other one is if you know, in the case where s is 1, then you get more simplification because then you don't have any denominators. So just kind of different ways of looking at it. Okay, that's it for today. Thanks everyone for watching. Have a good day.